All right, welcome to the Marine Amateur Radio Club. This is our uh, beginners level class. So I think everybody in the room is not a beginner. So, well, okay, so we have a somewhat beginner. Um, but this class will be some things that there may be more information than you want. There may be less information than you want. So feel free to jump in and ask questions and say, hey, what the heck are you talking about? Or how does that work? Or why is it that way? And I will do my best to answer. And hopefully, with the other people in the room, we can come up with an actual consensus of what the real answer is. So, but basically, this is our electricity and electronics introduction. So, what is electricity? So very simply, electricity is the movement of electrons. So if you've ever looked at like the model of an atom, you will see that the atom has a nucleus, which is tightly compacted, that is composed of protons and neutrons, and then floating around it in space is a ball of electrons that want to get close to it but don't. So there are subatomic forces that are at play here that say, hey, you've got to stay a little bit distance away from this, but not too far, right? And so there are some materials or types of matter that are good insulators. They're the ones that want to hold on to their electrons. Like they've got a tight grip on those electrons. The atom is going to stay inviolate as far as that material is concerned. Those things make good insulators because they do not conduct electricity. Electrons stick tight with their particular atoms. There are other materials that we call conductors that are perfectly happy to say, "Oh, you want an electron? Here you go. I'll get another one from somewhere else. It'll be fine. I will still have the same number I need. I don't have a problem giving you one and taking one from you." So, good conductors are things like gold. Gold is an amazingly good conductor. Um, Copper is a really good conductor. Aluminum is a pretty good conductor. You might notice something here. Most of these are metals. Silver is an excellent conductor. You might notice that most of these are metals, and that's because metals have this property where the position they are in on the periodic table lets them have like an extra electron that's kind of out in the wind somewhere. It's attached to the atom, but it's kind of on the edge, right? And so it's easy for that atom to get away. Now, good non-conductors or insulators are things like, let's see, I don't want to use a compound like glass, but silicon, right? Um, Glass is mostly made out of silicon. Silicon, where it's at on the periodic table, all of its little shells are full, and it does not want them to not be full. It wants them to stay full. So it tries to keep the atom, the electrons that it has, as close to its best as possible, right? And so it makes a very poor conductor, but in that regard, it makes a great insulator. We've established a number of alloys and things that make good conductors and others that make good insulators, and we use those all the time. So there are some important concepts with electricity that we're going to cover. They are specifically AC versus DC. Um, that's alternating current versus direct current. We'll talk about that in a sec. Charge, voltage, current, resistance, capacitance, inductance, and power. Now we're going to cover these not necessarily in that order, but we will kind of mosey our way through these concepts. All right. What we're going to do as we do this is we're going to use what we call a water analogy. Everybody's pretty familiar with flowing water, like from a pipe or a tube or something like that, or even a straw. And electricity works a lot like water in a lot of ways. It's different in other ways, and we'll highlight those differences as we come across them. But there are ways that you can say, well, if I've got water, I can think about what water does, and electricity kind of works in a similar fashion. So the water itself is the charge. That's the electricity, the electrons, the moving electrons, right? So that's the actual thing that's moving. And of course, when you're thinking about that, if I'm squirting water through a hose, the water is moving, the hose is not moving, right? So think of the hose as the wire, and the water as the electrons moving through the wire, okay? The voltage is equivalent to the pressure of the water, or how hard the water is pushing. So that can either be generated by a pump, which you can consider a pump of water to be similar to a generator or an alternator, um, or it can be like a big tank of water that's up high, right? If I've got a tank of water and it's here, it has a certain amount of water pressure that would be coming out. If I raise it up here and I'm still taking the water out down here, it's got more pressure, right? So think of that pressure as the voltage of the electricity, or the voltage as the pressure of the electricity. How hard is it trying to get through from one point to the other? And then the current is the actual movingness of the water, or the movingness of the electrons in the wire, or whatever is conducting them. If you think about that, if you're pushing pretty hard, your voltage is high, your current is going to want to be stronger. It's going to want to be faster, right? It's not really any faster, but it's going to be stronger. And then the resistance is equivalent to like the size of the pipe that the water is flowing through. If you've got a big pipe, you can pump a heck of a lot of water through it. If you've got a tiny little pipe and you're trying to put the same amount of water through it, what's going to happen? It's going to go much farther through the pipe out the other side. But it's going to, like, that resistance is going to slow that water down, or try to slow it down. Okay. So in our little diagram here, let me see, I've got my laser pointer. So you can see here, this is the water, and I've got a pump over here. That's like my generator, and it's pushing water through this pipe. And then I've got some sand in the pipe here. That's causing resistance. So that's trying to prevent the water from getting through. And then it's getting back up here to the pump again and being pumped around again. In a electrical environment, maybe I've got a battery that's producing the current. The voltage is how much is this pushing versus sucking, okay? Um, and when I'm pushing electrons through here, they're going through this wire and they're doing some work. In this case, there's a little light bulb here that it's trying to light up. And as they go through that light bulb, the light bulb acts like a resistor. And then it comes out the other side and it goes back into the battery. Now, we would draw that in a schematic diagram or a circuit diagram. This is the symbol for a battery. This is just an indicator of the direction of the current flow. And then this would be the resistor here, which is like the sand in the line over here, right? And so you'll notice we always have to have a circuit. If it's coming out of one end, it's going back in the other. And if you look at this in a schematic, you'll see that when you draw a battery, you have a big line and a little line. The little line is where the electrons come out, and that's the negative side of the battery. So a lot of people think, oh, positive side of the battery, that's where the electrons come out and they go around to the negative side. Actually, it goes the other direction. They come out of the negative side of the battery, they go through whatever is there and back in through the positive side. And then if you're comparing power versus energy, the power, which we measure in watts or kilowatts, if you're talking about a lot of power, is the flow rate of the water, how much water is running through our system, right? And the energy is measured in watt hours or kilowatt hours, and that's like how much water actually got moved. So you can't tell from this. You need something to collect the water in. So if you put your bucket here, how fast does that bucket get full? If I fill 5 buckets in an hour, I have more energy than if I fill 1 bucket in an hour. If I'm using kilowatts in electricity, I've got more energy passing through if I'm doing 5 kilowatts than if I'm doing 1 kilowatt. Okay. All right. Some of the terms that we use voltage, that's our pressure. And the symbol for voltage is an E, a capital E. So when people talk about voltage in a formula, they're going to use a capital E for that. Why they chose to use an E instead of a V, I'm not entirely sure. Paul, you might know.
Electromotive force.
Electromotive force is what the E stands for. Okay, so that's the pressure, right? And the unit of measurement is the volt, which was named after a guy named Volta, who developed one of the first batteries and discovered some of these original properties of electricity. And so they named the basic unit of electrical pressure after him, and we call it volts. The symbol that you use for uh, that measurement is a V. So you would have like 12-volt battery, you would put 12 and a V. Okay. Um, the current is the flow of the electrons. We use the symbol I for that. And that's measured in amperes. And there was a guy named Ampere who also was involved in learning how electricity worked hundreds of years ago. And so we named the flow of current after him. So the letter for that is A for ampere. And then resistance is the how hard it is to move those electrons, right? So a different material might have a greater resistance than another material. If you're looking at an insulator, it has an extremely high resistance. In fact, it's so high that it could be considered almost infinite. It's not. If you put enough voltage into it, it'll probably get through, but it really doesn't want voltage to go or electrons to go through there, right? So it's going to have a super high resistance. Something like a copper wire is going to have an extremely low resistance. In fact, you might even measure it and say, well, that's zero. It's you can't even measure anything. There's still a little resistance there, but it's so small you don't really measure it. R is the symbol that we use for resistance, and we measure that in a unit called ohms. And yes, there was a guy named Ohm that this was named. You're seeing a pattern here. All these things are named after people who were involved in this kind of stuff.
And symbol for resistance is omega.
Yes.
Nothing to do with the guy.
Which has nothing to do with ohm. I don't know why they chose omega instead of O, but that's what they chose, right? And then for power, power is the ability to do work, right? So remember we talked about the power being the fact that the water is rushing out of the hose and how much water is rushing out of the hose. That's the ability to do work. And the symbol for power is P, and we measure that in watts. Now, you might think, gee, was there a guy named Watt? Yeah, there was, James Watt, and he was big in steam engines. And first, we developed mechanical things before we developed electrical things. And so we were already using watts for power back then. And we said, well, we could just use watts for electrical power too. That'll work just fine.
He defined the term horsepower too.
Yes, James Watt defined the term horsepower, which was the amount of power or amount of energy a horse could apply in one day. Yeah. All right. Capacitance is the ability to hold a charge. And we'll talk more about capacitance in a minute because that can be quite confusing if you've never thought about what's going on here. But it's the ability to hold a charge. We use the symbol C for that, and we measure it in farads. Typically, we measure it in microfarads when we're dealing with electrical circuits that we normally work around with. But if you've ever seen a 1 farad capacitor, that thing can be quite beastly, and it can hold an awful lot of energy. Inductance is a resistance to change in current. The symbol for inductance is L, and we measure that in henries. And yes, there were guys named Farad and Henry as well. So all of these symbols are named after somebody who did some work on that. So as we think about our electricity, it's like water rushing through a hose. The voltage is how hard we're pushing the water. The current is how much water can we move. And the resistance is what's trying to stop us from moving the water through the hose. Okay. Those concepts are going to come back to bug us again more as we go through this. All right, so let's talk about AC versus DC. Now, what kind of electricity do we use in the house at home typically? We use both. We use both all the time. We just don't realize it. It's converted to DC, right? Yeah, so AC is alternating current and DC is direct current. Now, what that means is direct current means the electrons move in one direction. They move directly from the negative side of the power source to the positive side of the power source through whatever happens to be in the way, and they just go around that way, okay? In AC, we don't really do that. AC is like your outlet at home, right? These lights are probably, well, these lights are a bad example because these are LEDs and we'll talk more about that. But the concept is instead of pushing an electron all the way around the circuit from the negative terminal to the positive terminal, I'm just going to push it a little bit, and then I'm going to pull it back. And I'm going to do that again and again and again. And because I'm doing that, just like if I had water in a hose and I was shoveling it this way and then pulling it back this way, as I'm doing that to this water, the water over here is doing this, and the water further down is moving as well, back and forth. And when you get to the place where the work is being done, that water is like, oh, I'm going to push and then I'm going to pull back. And so you've got this kind of reciprocating action happening. This is basically what AC is. It alternates from going in one direction to going in the other direction. We typically will draw that, as you can see here, with like a sine wave. So you can see it's pushing and then it's pulling, and it's pushing and pulling, pushing, pulling, pushing, pulling. And this is the type of current that we use, or the type of system that we use for large amounts of power. And we like to use this because it's easy to change the voltage and current. We'll talk more about that as we get further along. But the concept is that AC, it does this kind of push-pull action where DC just pushes always in one direction. Now, why did I say we use both at home? All of your electronic devices are going to be using DC internally, even though you plug them in the wall. Like if you've got your computer and you've got a power supply, you plug that power supply on the wall, and then it has a little cord that comes out that plugs into the side of your computer. Well, it's AC up to that block, as Chris is showing us here. It's AC up to that block, but it's DC on the other side. Ideally, right? Yeah, that's what we like. That's what we want, right? And the reason we do that is because these electronic devices want to use DC. We could design them to use AC, but the concepts and mechanisms are much easier to do in a direct current environment. We will talk more about things that are running in DC as we move on. But you've got to keep in mind that there are differences between DC and AC. Now, when we're doing radio stuff, when you're like talking into the mic and that's getting converted into a signal that's going down the wire and ultimately out on the antenna, that's an AC signal. It's an alternating current happening, going through all of the system in your radio and out the other end. And when it's receiving the electromagnetic waves coming in on the antenna, those are coming in as an AC signal, and they're processed in that way as it goes through the radio. So keep in mind, even your little handheld is probably doing some AC to DC conversion all the time, right? All right. So let's dig a little deeper. So charge is like the amount of water that you have. So if you think about the stored power in a battery, like the water in a tank, if I've got one of these fancy schmancy lithium ion phosphate batteries that's got 100 amp hours of power in there, that's like saying I have 100 gallons of water in my barrel up above, okay? The more power you have, the more work you can do. So obviously with a barrel that holds 100 gallons of water, I can do more than I can with a barrel that holds 1 gallon of water. Same thing with your battery. It's not that I'm doing it all at once, but it's that I have that much energy available to work with, okay? When I run out of water or when I run out of electricity in my battery, I can't do any more work. I'm done, right? But I can pump the water back up into the barrel, just like I can recharge a battery. Now, can all batteries be recharged? Not really. Sort of sometimes, but it can be very dangerous to recharge a battery that's not designed to be recharged.
Especially efficient.
Yes. the old carbon zinc batteries, which were like one of the original battery technologies, they use a chemical reaction inside the battery to produce the electronic potential or the electron potential that wants to move those electrons around. Somebody, Dan's got his hand up. Go ahead, Dan.
If you could just take a note on the comments or the chat, I do have things that I'll be adding time to time. I don't want to bother the the actual presentation, so just watch the chat
Okay.
if you can do
I'll
that.
open the chat window up and I'll keep it up here.
Okay, and I do have something in there now. Thanks.
So Dan wants to note that in the club trailer that he's been building, everything is DC. Okay. So everything running in the trailer is DC. Now, Dan, I don't know, do we have an AC to DC power supply for external shore power in there?
Yes, I do have a 30 amp shore power connection and the ability to recharge the 200 amp hour lithium iron phosphate batteries via the AC. But
Okay.
that is
That's the limit of the AC in the trailer.
well, it'll do 30 amps, so we can ultimately the HVAC system will be running on AC, and so that will be the only thing that will actually require AC.
Okay.
So the
Cool.
AC will require AC.
Yes, the AC will require AC. All right. Thanks. Thanks, Dan. I'll keep the chat up in a little window here. Hopefully it won't go away when I click on my slides, but yeah,
Or
so
or I can just raise my hand when there's a chat in there, and you don't have to call on me. Just look at the
okay.
chat, okay?
Okay, that'll work. All right. So as we look at our display here, we see our tank of water. That's our battery, right? And the water is rushing down through this tube. There's a narrowing of the tube. That's my resistance that's happening here. And then the water is coming out at the bottom into this tray at the bottom here. So this is where the work is being done. It's being done by being forced through this narrow part of the tube. And the height of the water provides the amount of um, pressure that I have, and the tank of water, the amount of water in the tank is the total charge that I have to work with, or the total amount of power that I have to work with. Okay. So I can conceivably pump this water back up to the top, or I could fill a bucket with water and carry it up to the top and dump it back in the top again, right? They used to have these things called water clocks back in the day. And the clock was basically a big tank of water that would drip water on a little thing. And every time it would drip, it would count that. And some number of counts equaled 1 minute. And so it was geared up with some stuff so that as water dripped through here, the clock's hands would turn and it would measure the time. And that was great as long as you had water in the top. But of course, all you had to do was take the water from the bottom and pour it back in the top, and you could keep the thing going. If you ever let the top run out of water, the work would stop and the clock would stop, right? So interesting thing about water clocks there. So voltage is the pressure. So think of that as how high the water is above where the work is being done. Okay. How much water is pushing down on it. Gravity is providing that pressure in water. In electrical environments, the charge is providing that pressure. And so the particular composition of the battery or whatever you're using to provide the energy coming in is deciding what that pressure is going to be. So different battery chemistries have different amounts of voltage that come out of them. So your typical original carbon zinc battery would produce 1.5 volts of pressure or voltage. A nickel metal hydride battery would only produce about 1.2 volts of electrical pressure. And I don't know what the lithium chemistry actually produces, but in a lithium battery, typically they have a bunch of cells that are hooked together, and each one of these cells is producing this whatever level of voltage is coming out of them, 3.7. And then there's some control circuitry that modifies that so that when it actually comes out of the battery, it's 12 volts, because that's what we usually want, or 12.8 volts about.
Not exactly true.
No?
Usually put what they call a 12-volt battery in lithium iron phosphate at least is 4 3.7-volt cells. So.
And there's no controls on that. It's just whatever comes out.
It's just that it has a very flat discharge curve over most of its life.
Okay,
So 14.4 is the full charge voltage.
gotcha.
It'll eventually get down to 2.5 per cell or 10 volts right
Before it stops.
before it stops.
Yeah, okay, cool. All right, so the current, again, remember we talked about the voltage, now we're talking about the current. Think of that as the flow of water in the system, right? So the water is rushing through the system and it's flying out the bottom of this pipe. If my pipe is really big, I can push a lot more water out than if my pipe is really small. You can see that if I have two batteries that are producing different voltages, one of them is going to win, right? And typically what will end up happening is the one with the higher voltage is going to push backwards on the one with the less voltage and charge it back up again. So eventually you'll end up with them balanced and hopefully things will work well. But you got to watch that in a multi-battery system or a multi-cell system so that your cells don't get out of whack with each other. And if you have a dead cell in a battery, that can cause all kinds of grief. So that's typically how car batteries fail, is one of the cells has a problem. Jeff, you have a comment?
So on this slide, are you calling current voltage?
No, the voltage is the height of the water, the amount of pressure.
Right.
The current is the actual flow of the water,
He's calling current.
the movement of the water. Yeah, it's the amperage, right? Yeah, so think about that as the amperage of the circuit, right? So when I'm running a circuit at home, maybe I have a 15 amp circuit. I can't push more than 15 amps through that circuit or bad things will happen, like it will catch on fire. And so I don't want that to happen. So I put a circuit breaker in front of that that says, hey, if the current ever goes above 15 amps, just turn it off, stop it entirely. And so I care about the amps that are going through there. Now, the amount of amps that are actually going through are caused by the load, how much amperage it wants to draw, how much current it wants to draw, right? And again, the voltage is the pressure that's pushing this. So these concepts all kind of fold together, and you'll see as we move further on how this turns into actual work.
Jeff, I think what he's showing here is that you can overcome the restriction of resistance.
With more pressure.
more voltage.
Yes,
He's got more voltage on the skinnier wire. so
Yes.
Skinnier hose.
Sure. I thought that that's what we were talking about, but when you started talking about if we have more voltage and stuff,
no, I got you. Yeah, so you can see that with this one where the pipe is big, the voltage is going to deplete faster, right? Or the amount of energy, the water is the amount of water in the tank is the amount of energy of the charge that's going to deplete faster if I'm pulling it out really fast than it is if I'm pulling it out really slow. But because I've got more pressure here, you see these arrows are the same size. That's indicating that the work that they're actually able to do is similar. The voltage is higher, the current is lower, the amount of work is the same. Okay. We'll go into that as in with numbers in a few minutes. Okay. Think of the resistance as being like the diameter of the pipe, right? A wide open pipe is not going to produce much resistance. If I've got a kink in the pipe, that's going to cause some resistance. It's going to try to slow the water down as it's going through. So it's going to consume some of the current of the water. Okay. Same thing happens in the electrical circuit. Any load that you put on there is going to produce some resistance to the electrons moving through it. That's how it does the work. As it takes energy from the movement of the electrons and turns it into the work that you're trying to accomplish. Or heat. Well, producing heat is work, right? So if you think about like a very simple toaster, for example. The toaster has a heating element inside there. That is a high resistance piece of wire. It's usually made out of something like nichronium or something. And as you push electrons through there, they struggle to get through there. And in doing so, they give up their energy in the form of heat. And it's so much that it makes the wire glow inside the toaster. And that heat radiates off of the wire and heats up your bread and turns it into toast. Nice, yummy, hot, scrummy toast. Yum. I like toast, if you didn't know. Also, like in an incandescent light bulb, if you look at a light bulb without the frosting on the bulb, you'll see that there's a little wire that comes up, and then there's a little tiny wire that goes across this gap, and then there's another wire that comes back down. And that little tiny wire that goes across, if you like could zoom in on it, if we had zoom vision, you would see that's actually a little tiny coil of wire as it goes across. And the idea is that that's made of a material, what are they? Tungsten, yeah. And tungsten has a pretty high resistance. It's not high enough to be an insulator, but it's a pretty high resistance. And so as you push electrons through that little tiny wire, they get really hot. And as they get hot, the wire gets hotter and it starts to glow. At first it glows red and then it glows white hot. And as it's doing that, it's producing light, which is how our old incandescent light bulbs all worked. Nowadays, it's pretty hard to find an incandescent light bulb anymore, but we've gone over mostly to LEDs and fluorescent lights. But the old incandescent bulb, and you can still find them. There are still some out there. Some devices only work if you use an incandescent bulb, right? And so, like do you ever have an easy bake oven when you were a kid, or know somebody who did? The heat source in the easy bake oven was a 100-watt light bulb. And it was called a 100-watt light bulb was because it consumed 100 watts of power and produced that energy in light and heat. And the heat source was this light bulb inside the easy bake oven. It was hot enough to bake your little cakes or whatever that you were making in there. So if you put an LED bulb in there, it's not going to work as well as you had hoped. You're going to not get the nice yummy cake that you thought you were going to get.
You mentioned recharging carbon zinc batteries. You've ever seen one of those old school battery chargers where you put them in and close the lid and the light came on?
Yes.
That incandescent bulb was an indicator that it was charging, but it was also the current regulator.
Yes.
Because
as a resistor, it's going to limit the amount of current that you're able to pump into that battery.
well, it's a very special kind of resistor because when it's dark, its resistance is 1/8 of what it is when it's brightly lit. So as the battery gradually comes up in voltage, and
it slows down the amount of
the current flowing through it is less. The bulb gets dimmer, its resistance drops. So it has essentially the same amount of current going even when the battery gets close to full charge.
Yeah. All right, let's see. Let's go ahead and look at the next part here. So you guys have all heard of Ohm's law? Maybe you have, maybe you haven't. So Ohm's law basically says there's a relationship between current, voltage, and resistance. And the relationship is E equals IR. So the amount of voltage is equal to the amount of current times the resistance. And these, of course, these are in volts, amps, and ohms, right? So if you think about that, what does that actually do for us? That lets us say, well, if I know the voltage and the current, I can figure out what the resistance is. If I know the resistance and the voltage, I can figure out what the current is going to be, right? And so this little symbol here is what I like to use, is you basically put the E on top and the I and the R in these lower corners here. And if I want to know what the voltage is, I cover that up with my finger or whatever, and it's I times R, okay? If I want to know what the current is, I cover up the current, and it's E divided by R. And on this one, if I want to know what the resistance is, it's E divided by I. So it's a very simple way to remember that relationship and be able to calculate one of those values if you know the other two. Okay. We actually will see this again on the next slide in regards to power. Power being the ability to do work. It's a measure of the energy or mass moved over time. And that is actually the amperage of the current times the voltage gives me the watts of power. Okay. So in my 100-watt light bulb at, say I was at 100 volts, just to make the math easier, what's my current got to be? I need the current, so I have 100 watts divided by 100 volts, I get 1 amp. Okay. So my 100-watt light bulb is 1 amp of power. Now, if I had a 10-watt LED bulb and I'm still pumping 100 watts in there, I'm going to get 10 amps. Well, my LED bulb is not going to draw 10 amps. It's probably going to draw 0.1 amp. So at 100 volts and 0.1 amp, I'm really only getting, what am I getting? I'm getting 10 watts of power out of that. So that's why your easy bake oven doesn't cook your pie very well on an LED bulb, but it works great with an incandescent bulb. Okay. So this one also works the same way. You cover up the one that you want, and then these multiplied together equal this, or this divided by this equals this, or this divided by this equals that. So just a way to visualize that relationship. And it's also a pie chart, if you notice, PIE, it's a pie chart. Oh, all right. Okay, so that's the basics for electricity. Now, what we want to do is some more complicated things. So electricity basically gives you a very low kind of brute force ability to do things like heat something up or make something move. So like an electric motor will take the moving electrons and turn it into rotary motion, right? A light bulb will take the electrons and turn it into heat and then light. A toaster will take the electrons moving and turn it into just heat because that's all you care about. There will be some red glow, yes. With electronics, we want to do some more complicated things. And so electronics lets us do things with electricity in circuits. And remember, we were talking about the circuit having to be closed. It has to be complete. So you have to have a way to go from the negative side of your power source all the way back to the positive side of your power source. If you have a break in that, you're in trouble. Oh, let's see. Dan wants to know, is the pressure the same on each side of the kink? So if we go back to that right here, and the answer, of course, is yes, the pressure is the same. But if you notice, the speed as it goes through here has to be greater to push the same amount of water through. And then the water slows back down on this side. Does that answer your question, Dan? I hope so. Okay. Electricity does not slow down, nor does it speed up. So it has its own little properties, but that is a place where the water analogy breaks down. We're going to come back to the water analogy in a minute as we go through some electrical components or electronic components. But the basic concept that we need to keep track of is we're using the movement of these electrons to do things other than just push things around and heat stuff up. Okay. So we're actually trying to make some things happen that are not just heating things up or pushing things around. Okay. Electronics allows us to do that. And later we will take a logical step up from electronics and we'll talk about logic circuits. We will do that very briefly in this class because that is a much bigger chunk of worms than we have time for tonight. So, but let's go dive into some of our electronic stuff. All right. So basic electronics and schematics. We'll see you, Dave. Thanks for coming. You can watch the rest of this on the recording later if you want. All right. Take care. Dave has a bus to catch so that he can work tomorrow morning early. So he doesn't get to stay through the whole meeting, unfortunately. All right. So basic concepts, we have our battery, we have wire, we have resistors, we have capacitors, we have inductors, We'll talk about each of these in turn. Transformers, diodes, and transistors. On the logic circuit side, we have these different gates. You can ignore that for now. I'm going to come back to the logic side later, but again, very briefly. So the main thing to think of is each one of these symbols on a schematic means a particular type of component. Okay. And so we're gonna look at some schematics and see what we're actually talking about here. And we'll talk about what each of these types of components do as we go through this. All right. All right, let's go ahead to the next slide. So if you're taking the amateur radio test, when you're taking the technician test, there are some questions where you will be presented with a schematic diagram and you will be asked certain things about that diagram. Typically, there will be like one question on this. Now, it may be one of 4 different questions, and though that's why we have 4 things that are highlighted here. But in this simple circuit, we have a bunch of numbered items, and we're going to look at all of these as we go through. And I've highlighted the ones that are actually on the technician exam, just so that if you're only paying attention to pass the test, that will help you a little bit. But if we look at this, there's a few different things happening. One of the first things you'll see is this symbol over here. That basically means this is coming in from outside, okay? It's not part of this particular circuit, but electricity is coming in from somewhere else, okay? We have here this little squiggly line, that's a resistor. In an actual schematic diagram, there will be a little number saying what the resistance is. But in this diagram, that's not going to be there. You may be asked on the test, hey, what is component 1 in this diagram? It is a resistor, okay? The squiggly line is a resistor. This weird gizmo here with the 3 lines going in and out, that's a transistor. We'll talk about transistors in a few minutes. This dealy bop up here is a lamp or a light bulb, for example. There are different kinds of light bulbs that are represented differently. In this case, it's just a simple incandescent lamp. And then this over here, 4, is a battery. And you can see when you look at the battery, if you look back at this one, it only has like one little line and one big line. And remember, the little line is the negative side of the battery, and the big line is the positive side of the battery. So what's going on when there's 2 little lines and 2 big lines? This is actually saying that there are 2 cells in this battery, okay? So if you think about it, you have an electric cell that produces electricity. If you put more than one of them together, that forms a battery of cells. And that's where the term battery came from to mean this particular thing. Think of what's the other way that a battery is? Like in an artillery situation, each gun is a separate gun in the artillery battery. All of them work together to attack the target, okay? In a battery electronically or electrically, all of the cells work together to produce a uniform voltage between the positive side of the battery and the negative side of the battery. So each one of these cells maybe puts out 1.5 volts. If I put them together like this, I'm getting 3 volts out of the whole battery.
In some old schematics, for example, the early tube type portable radios that had a 90-volt battery, that was made up of 60 cells at 1.5 volts each. They would abbreviate and show 3.
Yes. Yeah, they're not going to draw 60 of them. They would, yeah, they would put a number here next to it saying this is a 90-volt battery, so that you would know what you were dealing with there. And then the last one is this number 5, which is like this little kind of wires going down thing. And that's the chassis ground. Now the chassis ground is different from the earth ground, and the symbols are different. And we'll see an earth ground in a minute. But basically what this is saying is in my chassis, I've got electricity that's going through some components, and then it's coming back through the chassis. So you can see this wire is not connected to anything, but remember, I have to have a circuit. These wires have to go in a circle, right? And so since both of these are tied to the chassis ground, all 3 of these are tied to the chassis ground, these are all essentially connected to each other. They just don't show them that way. They don't show a separate wire for that. Okay. So whenever you see these, think of them all as being connected together in this circuit. Okay. The other question that you will be asked potentially on the technician exam is, what does component 2 do? And the transistor controls the flow of current between the battery and the chassis ground based on the input signal through resistor 1. Okay, so what that means is, if you think about this transistor, we're going to dig more into what transistors do in a minute, but I've got this circuit here where current goes from my battery through the chassis ground, right? And again, the arrows wig you out because they don't always show you what's actually happening. And so in this case, you'll see this little arrowhead here. That's indicating that this is the emitter of the transistor. The transistor has 3 connectors on it. One is the collector, one is the base, and one is the emitter. And only in this case do you consider it as if it's moving energy from the plus side of the battery to the negative side of the battery. In reality, it's moving the other direction, okay? The electrons are moving from the negative side to the positive side. But this is the way we always draw it, and I don't know why. There's some historical reason why we do it this way.
When they made the mistake when they started calling the surplus of electrons positive.
Yes.
Or negative.
Yes. Yes. They thought that they thought it went the other direction, basically. And unfortunately, they thought that so hard that they made everything depend on that thought later. And when we later discovered that that's not really the way it works, but it really doesn't matter. The electrons still move around the circle, right? So, it confuses things. Anyway, so the electricity wants to go through this bulb and light it up, okay? And so as long as I have enough electricity going through the bulb, it will light up. And what I'm doing here, what the transistor does is it allows me to control electronically how much energy gets through here, depending on how much energy I put on this base side. So if I add more power over here, more energy will get through the transistor and the bulb will be brighter. If I have less power over here on the base, less current will get through the transistor and it will be dimmer. Okay, so that's what this is trying to tell you. And this is what the question is. It's really the other possible answers for this question are so dumb that you will recognize this and say, that makes no sense to me. This one actually makes sense. It's controlling the flow of current through the circuit over here based on the energy coming in from this side. Okay. If you take the technician test, there's another circuit that you may encounter, which looks like this. And in this one, we have an AC power source over here. So this looks like an AC outlet, okay? AC works a little differently from DC. And one of the differences, of course, is the electricity is going back and forth, right? It's not just going straight through the circuit. So that's something to consider as we're looking at this. But the parts that we see in this diagram, I've highlighted the ones in yellow that are on the technician test, or maybe on the technician test. The ones in purple, I guess that's kind of purple. What is that, hot pink? I don't know what it is. Those you might find on the extra exam. That's the only place where this diagram is used on the extra exam, is to say what kind of switch this is. Why? I don't know. I don't know why they do that. They could have just shown you some things and said, what is this? Anyway, so what we have here on this side of the circuit, we have an AC power source, and it's going through a fuse. So the fuse is a thing that is going to allow a certain amount of current to go through. And if more current tries to go through than the fuse will allow, what happens to the fuse? It blows. It stops conducting electricity. Okay. Usually this is a physical piece of material that if it gets too hot, it melts and it breaks the connection between the two ends. Now, if you're pumping enough power through, you could potentially bridge that gap and still get current to flow. But man, you would really know that was happening if that was going to happen to you. So in general, a fuse is designed to break the circuit if something goes wrong and too much power tries to get used. Okay. Then there is a switch, and this is a SPST switch. SPST says single pole, single throw. There will be different types of drawing or diagram for a double pole single throw or a double pole double throw switch that you may encounter. But in this case, this is a single pole single throw switch, which means there's only one input and one output, and I can only do one action. I can either close that switch or I can open that switch. I have a single action that I can do. I can modify that one. Then the next thing the electricity does is it goes through this side of a transformer. So this number 4 is a transformer, and it's specifically a transformer with a core. Okay. You can have a transformer that doesn't have a core. We're going to talk about what inductors are and how they work in a minute. But the basic concept is an AC will do this. DC won't do this. If you put DC through a transformer, you're just going to get the same DC. You're not going to get what you want coming out the other side, right? You won't get anything out the other side. But with AC, remember with AC, the current is going back and forth. So what happens in here is this side of the transformer, do I want to dig into this right now? Yeah, sure. This side of the transformer will generate a magnetic field, okay? And that magnetic field will increase in energy and then decrease in energy as I move my electrons in and out of it. And in fact, it will actually increase in energy and then decrease to zero and then increase the other side and decrease to zero, back and forth every time the electrons move back and forth. Your electric power in the wall is at 60 hertz, which means that it's going to do that back and forth dance 60 times every second. Okay. So think about how fast that is. You're getting back and forth every 60 times every second. What happens is, as it's doing this thing, this side of the transformer is called an inductor, and it's doing that and it's producing this magnetic field and tearing it down. And that magnetic field is causing a similar magnetic field to affect this inductor over here, which is actually causing current to appear and disappear over here as well. So because I'm moving the electrons on this side, they're making the electrons move on this side, even though there's no physical connection between this part of the circuit and this part of the circuit. Those electrons are moving back and forth on both sides. And the interesting thing about AC is if I have an inductor with some number of loops on this side and the same number of loops on this side, then I have the same voltage coming out as I have going in. If I have less loops on this side, I'll have less voltage coming out, but more current. Remember, the power is the same. If I have more loops on this side than I do on this side, I'll have more voltage coming out, but less current. And this is one of the cool things about AC is you can use a thing like this to change the voltage of your system within this transformer. And so you've all seen like the big transformers that they have at the power substation as you drive by, and it's like these huge boxes with all these huge wires coming out, and they're 10 feet apart because they arc flash and cause all kinds of problems if they were too close together. Basically what they're doing is when you have like a high tension power line, that thing's running at 300,000 volts, but you only want 110 volts on your outlet at home. So that is stepped down by one of these transformers to about 30,000 volts, which is then distributed through your neighborhood. And then there are those transformers on the pole, or they're buried underground quite often, or they're in one of those green cabinets that you'll see on the side of the road. And that will step it down to 240 volts. And that is what is actually delivered to your house is 240 volts. And it comes in, think about this inductor on that side of the transformer has one end and the other end, and then a tap in the middle. And that middle tap is the neutral. And so it stays at the same potential all the time. And the 240 is split between those two sides. So essentially what I get in my house, I get two wires coming to my house that are carrying 240 volts between them. And then I have a neutral wire in between that is at the zero potential. And in my circuit breaker box, I split that out and I say, I'm only going to use one power side on the neutral to run these circuits. And I'm going to use the other power side in the neutral to run these circuits. But I have some loads like my air conditioner or my range or my clothes dryer that want the full 240 volts. And I will bridge across both of the power sides and ignore the neutral entirely for those appliances. Okay. So cool thing about transformers. All right, so this is a transformer in this circuit. This is a diode, and a diode has the interesting property that it only allows current to go in one direction. So remember, in our AC, the current's bebopping back and forth here all the time. When it hits this diode, it only gets through if it's going one direction. So instead of getting back and forth, I get to this side and I'm going forward, only forward. Suddenly I'm at DC. I'm doing direct current, but it's still kind of pulsing. It's not steady. Um, there's a particular electronic component called a rectifier bridge that's made of 4 diodes that actually evens all that out and makes a nice, solid, simple DC current coming out. There's also some other components that have to be in there, like a capacitor and stuff, to help things smooth out. But so 5 is a diode, 6 down here is a capacitor, and you will see capacitors drawn sometimes with parallel lines or with one line that's curved. If there's one line that curved, this capacitor cares which is the negative side and which is the positive side. Okay? If it's not curved, the capacitor doesn't care. It works just fine either way. But that can be important if you're replacing a capacitor in a circuit and you put it in the wrong way. If it's one of these types that cares what direction it goes in, you can blow it up or things will not work the way you want them to. But 6 is a capacitor. We're going to talk more about these components in a minute, so don't panic. 7 over here is a resistor. And then this guy here is a light emitting diode. So you can see it's a diode symbol and it's got little arrows coming off of it. That's indicating that photons are flying out of this diode and producing light. Okay. This guy over here looks like a resistor, but he's got a little wire that pokes into it from the side. This is a variable resistor. And usually this is a device called a potentiometer where I can adjust, or a rheostat. I can adjust by turning a knob how much resistance this thing has. I can either make it more resistance or less resistance. Where would you encounter something like this? Think about a volume knob on your radio. Okay. A volume knob is basically a way to vary the resistance of that particular element of the circuit. And then over here on this side, I've got another diode, but it's got little tabs on either end. Okay. This is a Zener diode. And we'll talk about Zener diodes and other diode types in a minute as we go further on. And then, of course, we have our chassis ground. So remember, all these are connected as though they were all in the same, there was the same wire that was connecting these. When you see a line that looks like this with a solid dot, it means that those wires are connected to each other. If you see the line hop over another line, those are not connected. Okay. Even though they still cross, they're not really touching. It hops over the top of it. The ones that you care about for the technician: transformer, this guy; capacitor, this guy here; the LED, this guy with the arrows coming out of it; and the variable resistor, this guy with the arrow going into it. Okay. There's one other electronic circuit diagram you may see on the technician exam, and you'll notice a few things on this. Instead of having a battery over here, it's got this little squiggly line. This indicates that it's an AC power source. And then here's a capacitor that has a little arrow going through it. And you'll see this capacitor has straight lines. It doesn't care if it's one way or the other way. It's going to work the same. But I have a dial or a way to change the amount of capacitance of that particular component. That's what this little arrow means. Then again, over here, there's another capacitor, another variable capacitor. Down here we have an inductor, and it's a variable inductor. You can see the inductor is this kind of squiggly thing. Remember, we saw that in the transformer. This one side of the transformer is basically an inductor. Here's an inductor, but it's a variable inductor. I've got this coming back into it that says where to stop the induction happening. And if you look at it and think about it, what's actually happening here? If I had a coil of wire and I could put another piece of wire into the middle of the coil and cut it in half, the electricity is going to want to go the easiest way. So it's going to go through this and then duck out this way and go around the rest of it. If I move this arrow down, it's got to go through more of this before it can escape, right? So that's what the variable inductor is showing you. And then this item up here is an antenna. So you might think, well, this must be part of a radio. It's got an AC signal coming in. There's some stuff happening here with these guys. There's something going on with this. I don't really know what that's doing. And then there's an antenna out here. And so that's emitting electromagnetic radiation out into space or receiving it, right? It is an antenna tuner, yes. We're not going to talk about how that actually works in this class. We'll talk about it another time. If you're taking the general test, you may encounter this diagram, which is a little bit more complicated, but as you look at it, you will notice the symbols look pretty similar. There's some stuff going on in here that looks pretty much the same. I've got, what is this? This is a transformer, and you'll see this side has less loops on it than this side. Okay. I've got a transistor here. I've got resistors. I've got capacitors all over the place. I've got a lot of resistors, got a lot of capacitors. I actually have two different types of transistor. This one that has the vertical line and then the lines come out straight from it, that's what's called a field effect transistor. This one over here that has the lines come in on an angle, that is a BJT, bipolar junction transformer or transistor. And they use different technologies to make these, and they behave in different ways. That's why they're different symbols. Okay. The main thing you have to know is this one is a field effect transistor or a FET, and this one is an NPN transistor, it's a BJT, but it's not asking you if it's a BJT or not. So just remember, this one's an NPN. This one is a FET over here. Okay. And then, of course, you've got this diode. That's a Zener diode, and it's got the little wags on it. And then you've got this diode over here, which is a variable capacitance diode. So there's a diode and a capacitor, and they're hooked into one item. Okay. But it's still going to be the same parts of the symbol. The diode symbol and the capacitor symbol together. 3 down here is just a regular diode. Let's see, we talked about the Zener diode. This is the transformer. It's got this line in the middle, which means it's a solid core transformer. There's a piece of metal, ferrous metal in there that is helping the transformer do its thing. If you just had the two inductors and you didn't have that piece of metal in the middle, it would still be a transformer. It just would not have a core. Okay. And then this one, where is it? Number 7. Where are you hiding, number 7? Over here. This is a tapped inductor. And again, that's the same thing we were talking about on the previous slide. If I'm tapping this off, my electrons will take the shortcut. They won't take the hard way. They'll take the easy way out. Okay. Then there are capacitors on here. There's resistors on here. And there's even a variable resistor somewhere on here. You go find the resistor with an arrow in it. Number 11, this guy up here, right? Okay, so let's go back to the water analogy. This is where the rubber meets the road, as it were. We're going to go back to the water analogy. What works great with general electricity, it can be adapted to electronics mostly. Water doesn't always behave exactly the same as electricity does when we get down to this level, okay? But let's look at some water analogies of the circuits that we've talked about. All right, so a resistor. We already talked about this a little bit. A constriction in the pipe acts like a resistor, okay? So here's my tank of water. Here's my pipe, that's the wire. The constriction in the pipe is the resistor. And the volume of water passing through is the current, okay? In my circuit, I would have a battery, I'd have voltage going around, I'd have resistance, and it comes back into the battery. When you think about the variable resistor or varistor, think of it like a valve that can be opened and closed, okay? When it's open all the way, it has very low resistance. When it's closed almost all the way, it has very high resistance, okay? But you can think of it as the same way as like constricting the pipe with a valve instead of with an actual constriction of the pipe. And so your variable resistor is going to have a dial on it or some way to adjust the amount of resistance that is being produced by that device. Okay. All right. A diode, remember, a diode passes electricity in one direction only. So think of that like a check valve in your water circuit. Okay. If the water is flowing in this direction, the valve is open and the water goes through just fine, no restriction. If the water tries to go back the other way, the valve closes and it can't get through. A diode does basically the same thing with electrons. If the electrons are going in the direction I want, it won't let them, or it will let them. If they're trying to go the direction I don't want, it will stop them, it'll block them, okay? A light emitting diode will actually glow with a particular color when the current goes through it. And that's just a property of the materials that the diode is made out of. All right, so there's different technologies of diode. The ones that we usually care about are Zener diodes and Schottky diodes. Now, in your symbol table, the Zener will have those little tabs on either end. And a Zener diode will actually allow electrons to go in the wrong direction if the voltage is high enough. Okay. As long as the voltage is low enough, it'll act like a regular diode and they'll only go in one way. But if the voltage is too high, it will allow them to go the wrong direction, or the backwards direction. You may be thinking, why in the world would I want that? In certain circuits, you do want that. We're not going to get into the details of that, why that is, but that's a case. In a Schottky diode, the symbol actually, instead of having little tails that come off the top and bottom, it has almost like it's like a little S. So it has little curves that come back on the top and bottom of that line across the diode. And they have a very low current drop and operate very quickly. And it's because of the materials that they're made out of. There are certain cases where you want your diode to behave very quickly. In that case, you would use a Schottky diode as opposed to just a generic diode. And again, the Zener diode, it's going to do its weird thing where if the voltage is too high, it's not really a diode, it's just a piece of wire as far as the circuit is concerned. All right, capacitance is the fun one. Okay. Capacitance is a way of storing charge temporarily, very temporarily. Remember, the charge is like the amount of water in your tank. So the more water you have, the more pressure you have. What a capacitor does is it allows you to build up charge on that thing until it gets too big, right? If it gets too big, it'll actually, in our water analogy, let's picture we have this big tank of water and we have like a rubber diaphragm in the middle of it. I can pump more water into one side for a while and it will deform that rubber and hold that extra water. And then when I stop pumping it in, it'll push it back out because the diaphragm wants to go back to its normal shape. In an electrical capacitor, it's the same way. I can push electrons into it and it'll hold on to them for me. And then when I stop pushing them in, it will bleed them back off again. So remember in our circuit where we had our transformer and then we had our diode and then we had a capacitor, what's happening is on the other side of the diode, my electrons were going and then stopping, going and then stopping, going and then stopping. As they do that and they go into the capacitor, they go in and then they come out, then they go in and then they come out, then they go in and they come out. And what it does is it smooths out the flow in the rest of the circuit. Okay. Now, just like this tank with the rubber diaphragm in there, if I put too much pressure in there, what's going to happen to the rubber diaphragm? It's going to break. If I put too much voltage into my capacitor, what's going to happen to it? It's going to break. And when it does, there's usually a small puff of smoke. And we in the electronics business like to call that the magic smoke, because when the magic smoke comes out, it stops working the way you want it to. Okay. And it's very hard to put the magic smoke back into a failed capacitor or any electronics device, right? So that's just something to keep in mind. There are lots of different types of capacitor: electrolytic, ceramic, film, paper, silver mica, glass, and even vacuum capacitors. They are described by their dielectric, which is the material between the two sides. Remember the rubber diaphragm in between the two sides of my water capacitor? These different materials don't want, they're insulators. They don't want current to pass through, and they allow that charge to build up. Depending on what type of material I'm using, that's what defines what the capacitor is actually, how it is and what it behaves as and how it works and all of its little properties. They all are dependent on that dielectric material and the size of it and other things about its, how it's assembled and that kind of stuff. And if you think about that, essentially what it's doing is it's kind of balancing things out. Now, in this little circuit diagram up here, I've got a battery, I've got it connected to a capacitor, and I've got it connected to a resistor, and then an LED that's producing light. So this circuit is going to run just fine. What's going to happen at first is this capacitor is going to charge up to its maximum, and then it's not going to take any more. But because I've still got this pathway here, all those excess electrons are going to go through the resistor and into the LED. The resistor here is to make sure that some of them go into the capacitor by making it harder to go this way, right? They want to go this way first, but as this gets full, it gets harder to put more in. And eventually that overcomes the resistance of this resistor side and they go through the light. So now the light is lit up. Now, if I then take the battery away or disconnect it in some way, that charge is sitting on this capacitor and it will slowly bleed back out into the rest of the circuit, and it will make that light light up even though I've turned it off, and it will slowly dim until it goes out. So that's a place where you could use a capacitor for that. Kind of a cool little idea. If I didn't have this resistor, then I probably would end up with more current than this LED can handle, and it would probably blow up. If I didn't have it also, I wouldn't end up putting anything on this capacitor, and so it wouldn't do, the capacitor essentially wouldn't do anything. But because I have this resistor here, that's what makes this circuit work. So kind of cool. Fun stuff. All right. Next one is.
I've always been told that for best performance with capacitors, you should stick to your tongue immediately after disconnecting. I'm having the experience with that.
So if you are ever working on your air conditioner, there is a big honking capacitor inside the outdoor unit of your air conditioner, right? So what the purpose of this capacitor is to smooth out the current draw of the motors as they are turned on and off, right? And so those capacitors are sitting there and they will get charged up and allow the motor to slowly come up to speed rather than sucking a huge amount of power all at once and blowing your circuit breaker. Now, whenever you're going to work on one of these things, the very first thing you want to do is discharge that capacitor because there's a lot of energy sitting in there. Now, if you left it just sitting there over time, that energy would bleed out and eventually the capacitor would be discharged. But if you have just turned this thing off and you're about to go touching it, you want to discharge that capacitor. Another place where this used to happen a lot was, remember the old TVs that had a CRT in them? That CRT is like a giant capacitor. And when I say giant, I mean like 15,000 volts giant, right? And so the first thing that you do before you work on a tube of that type is you discharge the capacitance inside that tube. And there's a little wire that runs from your flyback transformer back up to your tube that goes inside the tube and connects to the grid in front that builds the electrical potential that makes the tube work.
Actually, the capacitor, there is a separate capacitor.
There is a separate capacitor as well, yes. But yeah, so The thing is, you don't want to be monkeying around inside your old TV unless you discharged that tube, because otherwise it will very happily discharge through you. And trust me, you do not want that to happen.
And those can hold a charge for months.
They can hold the charge a long time. Yeah. So even though that TV has been sitting on the shelf at DI for 6 months or a year or 2 years, it might still have a charge in it, especially if some dope has plugged it in and tried to turn it on and said, well, this doesn't really work.
Also applies to the old CRT monitors.
Yes, anything with a big tube in it, big, yeah, oscilloscopes, anything like that that's using a display tube like that.
Wires.
The other place that you will encounter capacitors is in your car, because you want to generate a spark in each spark plug. And so there used to be, in old cars, there was a single coil and a distributor that would feed that voltage into each spark plug in turn as the engine was running. And so if you're mucking around with that, you want to make sure you discharge that coil before you start disconnecting things and taking spark plugs out and stuff. Nowadays, they typically have a separate coil for each spark plug. And so it's much harder to kill yourself with than the old systems. But yeah, you could really hurt yourself badly.
Now you just have to watch out for the fan.
Now you watch out for the fan. Because the fan might turn on at any moment, even if the car is turned off. It's really counterintuitive, right? But let's wait for our fire department to get dispatched. Ooh, apartment fire, that's not good.
On November 5, near 35, West, Battalion 81, Battalion 11, Ladder 40.
This will take a second. Man, they're calling them all out.
17, and Battalion 17, respond to apartment fire at 4267 South Twin Riverway. Respond on November 5, near 835 West, time of 1952.
Ugh. Not good. Apartment fire somewhere. Okay, so the next one we're going to talk about is the inductance or the inductor. Remember, we talked about this little coil of wire and how it builds up this magnetic field and tears it back down. You can think of that in the water analogy as a water-driven flywheel, okay? So as I start pushing water into this thing, it's not moving at first and it resists moving, right? As I push water into it, it slowly starts speeding up as it allows the water to go through. And then once it gets up to speed, it's essentially not restricting me at all. It's just spinning happily and water is going through without any real resistance until I stop pumping water through. And then, of course, it wants to keep spinning because there's a big flywheel attached to this thing. And so it wants to keep pumping water even though I'm not giving it anymore. So it causes more draw that takes time for that to come out. In an electronic circuit, a coil of wire like this is essentially an inductor, and it does the same kind of thing. As I push electricity into it at first, it resists me and tries to stop me from doing it. As it builds up this magnetic field, it resists less. And then at some point, if I stop pushing power into it, it wants to continue power going through it. And so it makes that continue to happen as the field collapses and it drops back down to zero. Now, we use that in a transformer because we depend on the fact that not only does moving electricity generate a magnetic field, but a magnetic field generates moving electricity, okay? So I put two inductors next to each other or wound together with each other, and as I energize one coil, the other coil becomes energized. As I de-energize the one coil, the other coil becomes de-energized. And remember, in our transformer, if we have a different number of loops in the one side than we do in the other side, that's going to want to change the amount of pressure that's going through from one side to the other, okay? Inductors are pretty cool. They're pretty weird. They're hard to understand. But as long as you understand what they're doing, you don't really need to understand why or how they do it. It's just the fact that, yes, this is what it does, and I depend on its side effect that this is what happens, right? I don't really care how it happens, but that's what it does. Now, you are thinking, well, gee, don't capacitors do the same thing? They store energy and then release it after it stopped going in. Well, they do kind of. But remember, the inductor uses a magnetic field to store that energy and the collapse of that magnetic field to release the energy, where a capacitor store it as an electric field. Okay. And when you think about the reactance, which is the amount of resistance that's happening, is this as capacitors are are charged and discharged faster, the frequency of doing that goes up, their reactance decreases. But inductors, it's the other way around. The faster I try to do that change, the more it resists the change. Okay. So there, it's like the opposite of a capacitor because it's using this kind of magnetic side of the thing rather than the electrical side. Uh, Again, these are really weird when you start trying to think, how does this actually work? What's actually happening in here? Don't worry about that part. Just know that it does what it says it does on the tin, and it will perform in the way that it's supposed to. All right, the last one we want to talk about are transistors, and we have like 3 minutes. Let's see how fast we can get through this slide. So your transistor is like a variable valve that's controlled by another signal. So remember in my varistor, I could adjust my variable resistor. I could adjust the amount of resistance by turning a dial. What the transistor does is gets rid of the dial and allows another circuit input to control what's coming out. And you're thinking, well, why do I care about this? Well, I may have a very weak signal that I want to use to control this, but a very powerful signal that I want to control. And the transistor is happy to let you do that. In our water analogy, I've got some amount of water pressure here, and there's a valve here that is open and closed by that water pressure. There's bigger pressure on this side, on the collector side of this. And as I open this valve, that is able to come out the emitter side, right? If I reduce this energy on the base, this valve gets more closed together and less comes out, okay? So where can I use this? The typical place we see this is an amplifier. I have a very weak signal from my audio, from my microphone, but I want to control 100 watts of power that's going out of my radio. With transistors, I can do that in an electronic fashion without any monkeying around or anything. It's just going to do it. Now, obviously, we're not going to pump 100 watts through a transistor, but we'll start with whatever it is, maybe a watt, and then we'll amplify that until we get to the level that we want to be at. There's two basic transistors that we normally talk about, and these are the BJT, the bipolar junction transistors. You will see NPN and PNP. Now, the easy way to tell these apart is NPN stands for not pointed in, so the arrow is pointing out, and the PNP is pointed in, so the arrow is pointing in. And if you think about this, it goes the opposite direction, right? So again, remember, we're talking about this as positive on this side and negative on this side. In reality, it's going the other way against the flow of the arrow. But because of the way the nomenclature is, we draw it the other way around. But if I have an NPN transistor, my collector is over here, and the signal on the base controls how much gets emitted. If I'm in a PNP, the collector is over here, and the signal on the base controls how much is emitted. The difference being in an NPN, a positive voltage on the base allows current to flow out. In a PNP, I'm pulling voltage from the base to cause the voltage to go through. So depending on how hard I pull, it controls how much energy goes through the transistor. On this one, depending on how hard I push, controls how much energy goes through the transistor, okay? These have pretty much replaced tubes in modern electronics. Interesting fact, they used to call tubes valves, and the British will still call them valves. And they act like a valve in a water circuit, an automatic valve that you can control with another signal. That's essentially what transistors are doing. Okay, they're like little tiny valves in our water analogy. There are different kinds of transistors that are used for different purposes. We talked about the BJTs, the bipolar junction transistors, which are the NPN and PNP types. There's also FETs, or field effect transistors. These are field effect transistors. Some of them will be called MOSFETs. You'll hear about, oh, that's a MOSFET. It's a metal oxide semiconductor. And then you might have just a JFET, which is a junction type. And so they basically do the same kind of thing, but their nomenclature is a little bit different because the way they operate is a little different. And then you have these IGBTs, the insulated gate bipolar transistors, and they're drawn again a separate way. They have the gate is separate from the base. Okay, so it works the same way, but there's no physical connection between these two sides. There's an insulator in there, and that can be important depending on how much power you're pushing through this thing. There are other components that you will encounter, and you'll see we're not going to go into that right now. The last slide I have is about logic circuits. I don't have time to go into that. We will do a separate class on logic circuits and how we do things with them. And we'll talk about digital stuff, and we'll talk about how computers work and all of that stuff. We'll do that in a different class another time. But you will encounter these logic gate symbols, and they're basically, there's like 8 different types of logic gates that do different things. And these things are made up of transistors and associated components. So when we get to this, we'll actually talk about what's inside an AND gate and what's inside an OR gate and how does it actually work electronically. And then we'll talk about what we can do with the logical nature of this. We won't do that today. That's what I've got. Any other questions or comments from anybody? Dan asked, is the ferrite core like iron clay? I really have no idea what a ferrite core is. He says, what's the difference between an iron core and a ferrite core? I thought ferrite is iron. Paul has an answer for us.
Okay, in a transformer with an iron core, in addition to doing its magnetic coupling of the input coil to the output coil, eddy currents flow. It creates currents that flow in the iron itself, and that's wasted energy. Ferrite uses ferrous metal particles suspended in an insulator to provide the magnetic part without allowing the current to flow.
Okay.
In the core.
So in case you guys couldn't hear that on the Zoom, the difference is, like, if you think about your transformer, if you have an iron core in the transformer, you're inducing a current from your inductor on the one side. That will actually induce a current flow inside the iron core, which is wasted energy. Okay. And so that will then induce the current flow on the other side, and out your power goes, but you're wasting energy by moving current within that iron core. What the ferrite core does is it suspends iron particles within an insulator or a non-conductor. And so you get the magnetic field supported by that because of the iron, right? But you don't get the current because the iron isn't able to transmit the current. It's kind of trapped or held in place by this insulator.
So
And
it is like iron clay.
So it is like iron clay, sure.
Yeah, okay.
The different numbers after it are the different makeup of that.
So Russ adds that if you're looking at a particular ferrite core, it will have some numerical value on it that indicates like what percentage of iron is in there or what percentage of non-conductor is in there. And that will help you to identify the properties of that iron core, right? Sometimes you may want an iron core because you may want to waste that energy in a particular way. I can't think of a place where you would want to do that necessarily, but you could.
Ferrite became popular when we started trying to transform radio waves, because in a AC line like 60 hertz, iron still works because that core can't support, doesn't
It's not fast enough.
Yeah, doesn't work well enough to take a lot of energy. But at RF, you can't get it through the core.
Right.
It basically just hits the core without ever getting to the other core.
Yeah. So Paul brings out that when working with electricity at 60 hertz, the iron core is perfectly fine because you don't have enough, your current is not changing fast enough to really induce that voltage within the iron. But when you're talking about RF frequencies, where, we're talking in our VHF, we're talking even hundreds of megahertz, right? And even HF, we're talking in tens of megahertz or thousands of hertz, Yeah, we're talking a lot of stuff going on, right? And so that's where the ferrite cores came into value, is that it basically reduces the ability of the changing signal to induce that current in the core. So it ends up turning into heat, which is wasted, but that's we waste a lot of energy as heat. Ask me sometime about braking in cars, and we'll talk about heat being wasted. Okay. Anyway, that's what I have. Other questions, comments? No, I'm going to stop the recording. Let me find the button.